Several initiatives have been started, and out of that, one of them is the PRL Amrut Vyakhyaan, wherein we invite people of eminence in the fields of science, engineering, technology, arts, literature, business, and law to share with us their excitements in their respective domains so that we can enhance our knowledge. This Herculean task, which started on the 4th of August 2021, continued uninterruptedly for 75 weeks, and we had celebrated the 75th PRL Kamrit Vyakhyaan, a landmark event, on the 5th January this year. All the lectures delivered so far are available on the PRL's YouTube channel, and I encourage all of you to view these exciting lectures. Buoyed by the success of the PRL Kamrit Vyakhyaan series and several encouragement that we have received, it was decided to continue this series at a monthly interval after the 75th event. In that regard, today we are having our 77th PRL Kamrit Vyakhyaan, which will be delivered by yet another eminent scientist, Professor Mahesh Anand, who is from the School of Physical Sciences, the Open University, UK. He is a world-renowned expert on lunar science, and he is going to deliver his Vyakhyaan on an interesting topic, Apollo to Artemis, the science and exploration of the moon. On behalf of PRL, I thank Professor Mahesh Anand for kindly accepting our invitation and agreeing to deliver this Vyakhyaan. To formally introduce the speaker to the audience, I will invite my colleague, Dr. Megha Bhatt. Dr. Megha, please.
Thank you, Dean PRL. This is an opportunity for me to introduce Professor Mahesh Anand, also my colleague. He has a very long list of awards and achievements, so I will not be able to go through the whole, but I will be giving a very brief introduction about him. The most important thing which I would like to mention first is that he really liked with the young researchers, and he's mainly here for that purpose because he really finds that future is here. And many of his students are actually at leading positions now in different universities and research institutes. So Professor Anand received his bachelor's and master's from India. So bachelor from BHU and master's from IIT Bombay. He did his PhD from University of Cambridge in UK in 2001. And before joining the university, Open University, he also worked at University of Tennessee in USA and at the Natural History Museum in London. About his research, so Mahesh is very rich in terms of having a range of extraterrestrial samples from Moon, Mars, and asteroids. And the main research focus is to understand the formation and evolution of the solar system. And in this journey, he has guided more than 30 PhD students and postdocs. So he is leading a young group there at his university. He has published more than 100 papers in very high impact journals. He has edited several books, and his other research interest that includes application of scientific knowledge derived from fundamental research to inform planetary exploration programs. Professor Anand is currently chair of UK node of NASA Solar System Exploration Research Virtual Institute Survey, which comprised over 100 members from 15 UK higher educational institutions. I also want to mention that he is a co-founder and co-chair of annual European Lunar Symposium, And he has contributed to several committees, and he is continuing that. And so the list is really long, and I just end here because I know that everyone is very interested in knowing more about your research. So with this, I invite you to dais and please deliver your lecture.
You want to turn the lights down a bit? Okay, thank you. So first of all, namaskar, everyone, and good afternoon. Great to be here. I would like to thank your director. Anil cannot be here. He had to rush to the airport, but he has been very kind. He spent a lot of time with me since I arrived last evening, and I'm so glad to see so many of you interested in coming and hearing what I have to say. And I was also very impressed to hear about this lecture series. And it is always good and great opportunity to stand on the shoulder of giants. I think that's what I'm doing. We already had 75 excellent seminars, plus one, and I'm the next one. And I'm here to talk about the future. There's nothing better than actually building on the past and looking forward towards the future. Okay. What I'm going to do is, and by the way, welcome everybody who is joining us online. I haven't forgotten about you, but hopefully you can also interact and engage in the same way that the audience here in the seminar hall could. My hope here today is to give you a flavor of the variety of research and various other opportunities I have received in my journey in academia so far. It was only 26 years ago that I was graduating from BHU and moving to IIT Bombay. Up until then, I had spent all my life in Varanasi. So I'm through and through a Banaras boy. So if you ever want to communicate with me in Hindi or Bhojpuri, feel free. Okay? And I have a very strong connection to Banaras, of course, but to my homeland, okay, in India. And what I would like to do is to share with you all my personal journey in the hope that you find it useful. And if any of you get inspired by any of that to do whatever you want to do, you don't have to do what I have done. It will be an honor to have actually influenced somebody in my career. So as Megha had very kindly introduced me, I still cannot skip this slide, which essentially gives you a few pointers as to where my journey began. Born in Varanasi, stayed there for first 23 years, and then moving on to IIT Bombay opened limitless opportunities for me by bringing me in contact with lots of very talented people from around the country, and then subsequently provided a springboard for me to go and actually see what is there out in the world by getting a Cambridge Nehru Scholarship at the University of Cambridge. And I'm ever so grateful for Cambridge Nehru Trust, because I could have never been able to afford, paying for a PhD degree. So somebody somewhere was very kind to me, and I would like to return that favor to how many people I can. After finishing my PhD, I crossed over, as we call it in the UK, crossed over the pond to America. And at that time, I had just finished my PhD in traditional area of geoscience by working on the evolution of sedimentary Kadapa Basin, which is not very far from here. But I was introduced to the fascinating world of diamonds and moon rocks. I mean, what more can you ask, right? It was Professor Larry Taylor who you see there. Picture, actually, I took this picture of Larry, and I know Amit is here. Amit also worked with Larry. And Larry was a great character, and he worked hard and he partied hard. So we really got on well. And Larry introduced me to mantle xenoliths from Siberia. I started working on diamonds in those mantle xenoliths, and I was telling one of your colleagues that I spent some of my time polishing diamonds because the idea was to actually expose the mineral inclusions in diamonds for in situ work. And simultaneously, he asked me if I would like to work on lunar samples. And for me, it was like, here in India, what you would say, you go to a mithai dukan, huh? And you see so many sweets. And if somebody asks, would you like to that, you say, yes, everything, right? So it was like the same thing, kid in a candy shop. Given the opportunity, you want to grab it. And while doing that, always I like to think that there is always something new to find. So never accept if somebody says, that's not worth doing it. Everything is known in that. Clearly, they don't know enough, right? There's always something new to discover. And the evidence of that was one day, while actually looking at a thin section of a lunar meteorite, I stumbled upon a mineral that had never been found before. So I not only contributed to the discovery, I was able to name it after a very eminent professor who had been talking about the process of space weathering on the moon and on asteroids. And we thought that this mineral was as a result of a space weathering process on the moon. And therefore, it should be named after Professor Bruce Hapke, called Hapkeite. But then, as many of you would recognize, life is no fun by yourself. You want a companion. I did have a companion. And when you have a companion, there are lots of fun, but also there are some other constraints. And one of those is that in this virtual world, we still want to be together at some place physically, right? And my other half was actually finishing PhD also in Cambridge and then moved on into Netherlands. And I was in America. So we were looking for opportunities closer. A new job opened up in Natural History Museum in London, which I applied, and I was successful. So I moved back to the UK, where I was then given the chance to work on the famous collection of Martian meteorites at the Natural History Museum. And not only that, my office was right there. So every morning you would walk in front of this beautiful building. And then even better, when Christmas time came, everybody went home, I could still come and work. And I remember that on a Christmas day, I would be walking through the hall where you have the famous Dippy the dinosaur, another dinosaur skeleton, and you are walking through it. And yeah, it's a real feeling, it's a night in the museum sort of thing. So again, I was just trying to soak in whatever was there while learning new techniques and new problems to solve. But at some point in your life, you need stability. You can only be doing postdoc for so many years, and that's well known in academia. You do first postdoc, you do second postdoc, and by the time you think, okay, now it's time to, put the anchor down somewhere. And the Open University that I had never heard of, to be honest with you, had just advertised 5-year research position, which were called academic fellowship position. And my postdoc advisor at the museum, who herself was just appointed as a professor at the Open University, said, Mahesh, would you like to apply for that? It is a very good job. I said, yeah, why not? And then when I found out what actually Open University had, I thought, why didn't I know about it before? Because it had all the analytical instruments that a geologist or geochemist or an isotope geochemist would like to have. And long story short, I was offered the job, which I very gladly accepted. And then here is the building that I'm based in, and Neeraj and Megha have already visited us last November, so they know where we are. We spent a bit of our budget on art installation, which we spent on putting these landing lights on in case Martians were ever landings they needed to be guided. So one thing the OU, or the Open University, is very famous for those who know Open University for its research, is its cosmochemistry or isotope geochemistry laboratories. And many of those are custom built. So here is one of our colleagues, Sasha Warshawski, who has actually built a mass spectrometer, we call it Finesse, which can simultaneously analyze your carbon, nitrogen, its isotopic composition, plus some noble gases. And I'll tell you a little bit more about it later. So this is one of the unique things about the OU, that we don't just buy off-the-shelf equipment, we build our own. And we not only build our own for laboratories here, we build laboratories to take to other worlds in terms of payloads to Moon, Mars, comets, etc. So that allows us to actually interact with scientists, engineers, to a whole range of people who otherwise might not work together. And Megha mentioned about the European Lunar Symposium. I'm very passionate about communicating my research or the wider research that is going on around me to not only people in my field, but also with other stakeholders, be it public, be it policymakers, whoever they are. Because at the end of the day, I am being paid to research grant to do a piece of work that has to ultimately feed into the betterment of the society. Of course, knowledge gain is there, but also there has to be some other tangible benefits. And for that, we need to communicate with every stakeholder. And one of the ways is to actually bring the communities together, first of all. So I said in Europe, there wasn't anything happening about the lunar science and exploration in particular. And so I co-founded this meeting that is happening every year, where about 150 people from all over Europe and some from the US come and discuss everything and anything to do with the moon, not just science, exploration. And now you have heard that there is also commercial interest in going to the moon for resources and other things. So it is actually increasing in size. And this year we will be holding that meeting in the beautiful city of Padua, near Venice. The abstract deadline is still 2 weeks away, so if you want to participate, you are welcome to. I'll show you a slide towards the end. And none of what I have achieved so far and what I'm here to talk to you about would have been possible without my team members. And here are only a few pictures who I could find. There may be many more, but all the PhD students who actually came, and then when they left, they were experts in their field, and now they are making their own mark in the world in their own way. Postdocs, and of course, other senior colleagues who have supported me throughout this journey. So all the work that I will be presenting, somebody somewhere in this collage has been involved, plus a few more who are not onto this screen. So I owe it to them. So very briefly, space research at the Open University is comprised of about 100 researchers, and including 60 or postgraduate students, like PhD students. It's not a huge group, it's not a huge team, but it's a modest size team. It is the third biggest group in the UK, from one of the metrics. We have few disciplines, such as astronomy, planetary and space sciences, which is what I'm here to represent, and space instrumentation. And also we have a new center for astrobiology that is interdisciplinary center between earth sciences, planetary sciences, school of law, and social sciences, etc. So it's quite a happening place. But if you work on space missions, it sometimes can take years, if not decades, to actually start from conception to fruition. And here is an example, or a couple of examples of those where you might have heard about the European Space Agency's Rosetta mission, which chased a comet and tried to put a lander on the comet called Philae. And at the OU, we actually were involved in building a small payload that was on that lander. And the lander, unfortunately, did not quite land the way it was intended to, but still some measurements were made and some science advancements were made. Very tricky process. The whole project took nearly 30 to 40 years from the day it was conceptualized until the landing. So that's how long it takes. So you have to also keep yourself busy with other things. Once the mission has actually launched, you are very busy until then. But then if it takes 10 years to get to your destination, you've got to do something else for 10 years to do it. So we've got multiple projects going on. We also have Cassini-Huygens involvement, where the Huygens probe dropped a science package onto the Saturn's moon Titan. We had an equipment that was again built at the OU. ExoMars is a program of the European Space Agency to explore Mars, of which the target is to land a rover, which is now renamed Rosalind Franklin, to land on Mars. Unfortunately, it was a joint program between ESA and Roscosmos, the Russian space agency. But last year, when the Ukraine-Russia war broke out, that relationship had to be revisited. And now the plan is to actually send ExoMars rover with NASA, but that's going to take 5-6 years to actually repurpose the platform on which this lander would be, a rover would be sent. It will be 2028 timeframe. But a part of that mission called Trace Gas Orbiter is already there around Mars and sending data, and much of the science is being done. And we have an instrument again on Trace Gas Orbiter that was built at the OU collecting data. So these are some of the mission involvements that my colleagues have. Coming closer to what I do, the aspiration is to do world-class research because you always have to aim higher. There is nothing like national, there is nothing like transnational. It has to be the world leading. If you're doing research, it better be world leading. So that has to be the aim. And that's the ethos with which we work. And we have been very privileged to have access to Apollo samples that were collected by the Apollo astronauts. So we get samples from NASA to do our research. We have a huge collection of meteorites in Natural History Museum, but at the OU as well. The OU has the second largest meteorite collections in the UK. And quite often, lots of meteorites, they come unannounced. And we drop everything and then we focus on them and try to get more science out of them. And at the end of your research, you also have to publish your research because that's the gold standard in the community. That is one of the outputs. It's not just good enough to do a research, a good piece of research, but you have to channelize it so that the output is communicated to whoever is your audience. So in this case, that means publishing a number of papers. And right now, I'm also involved in China Chang'e program with colleagues at Chinese Academy of Sciences, where we published a Nature paper last year. And we have another paper which is going to Geoscience in a couple of days, hopefully, but unfortunately, I can't talk about the results in this talk, but it will be an interesting one. So, let's see what we are talking about. We are not just talking about the moon. The moon has been an integral part of what we call the Earth-Moon system. So the moon cannot be studied in isolation. You can study the moon, but I think we would be missing a trick if we didn't use that knowledge to extract information about our own Earth. Because it seems the moon and the Earth have had a shared history. It's up to us to actually deconvolute that information that is recorded in pieces of rocks that we as geologists, we go out either collect or astronauts bring to us, or they come to us as meteorites. It's really a detective's work. And the good thing about the moon is that it's relatively near. Yeah, compared to Mars, where it takes at least 6 months to reach, you can reach to the moon in 3 days, right? And you can come back in 3 days. Whereas for Mars, the whole journey could be as long as 2 years. Yeah, so there are lots of challenges and things. And as I said also, because the Earth and Moon have had a common shared history by studying the moon, you also are learning about what was happening on early Earth, for which there is barely any record left on Earth because of plate tectonics and other weathering and erosion processes. So moon has many ways of actually teaching us about itself, about the Earth, but then you use that information to say what was happening in the solar system. Yeah. So you then start to actually develop understanding of the wider solar system, develop hypotheses. How are you going to test those hypotheses? The Mars sample return or any future sample return from any of the Jupiter's icy moons, or even, sometimes we have talked about Venus sample return. These are all driven by the knowledge that we have derived by working on lunar samples, essentially, one way or the other. Now, before we go next 50 years, we have to look back at the previous 50 years. And this is what essentially what you see on a nice clear night when it's nearly full moon is the near side, because the moon is tightly locked with the Earth. And those are the positions or places where actually the Apollo missions landed. You can see that these are mostly equatorial regions, and they are onto those dark patches, which are known as mare. And that's a Latin word for seas, because olden days the astronomers thought that there were seas on the moon, and it turned out that they're not seas, but actually they are vast plains of lava flows. Okay, so most of the Apollo missions had to land somewhere safe. They had to land somewhere where they can communicate with the Earth. The easiest places were in the equatorial region. Okay? We have a lot of samples from these regions, but also the knowledge that we have gained in the last 50 odd years could be biased if these samples are not truly representative of the global world. So that's the question now we have started to raise, because we have now much more information, particularly from orbit, because we didn't have the global coverage of the moon using satellites in the Apollo days. Yeah. So if you were doing the lunar exploration today, you would do it the way we are doing it now, is you collect the global remote sensing data set to build a global picture to then go into details. But Apollo was done in a geopolitical time where it was a competition to get to the moon first and come back, and therefore it did not quite happen that way. Chang'e 5 is the highest latitude landing on the near side so far, but it still is one of the Mare regions. Certain different characteristics and much younger lava flow, but essentially lava flows. This is how the far side looked like in 1959 when the Luna 3 flew by, and this is how it looks today based on the data from the LRO mission. And you can see that Chang'e 4 has landed on the far side into an area which is known as the South Pole Aitken Basin, which you can't see very well here, but if you focus enough, you will see that there is a dark patch there, which will be outlined in the next image, and you can see that better here. So this is the near side and the far side topographic maps. And the total elevation difference, the deepest point to the highest point, is about 13 kilometers. So the relief is about 50% more than the height of the Mount Everest. Okay, so moon is not so simple place. There are lots of variation. And the South Pole Aitken Basin stands out very much when you look at the topographic map on the far side. And right now, lots of missions are planning to go near the South Pole to get the samples from the South Pole Aitken Basin, but particularly also to look into some of the craters which are near the poles, either north or the south, particularly on the South Pole, to look for water ice which might be preserved there. And I'll talk about that in a little while. So my research has been mainly focused on lunar samples. So we need to know how many types of lunar samples do we have, what are the different sources that provide us the samples. Of course, the 6 Apollo missions are the main source. Almost 400 kilograms were brought back. The lunar missions only brought back 300 grams, but nonetheless, they were quite important because they were from a different areas of the moon. But not much work has been done on them, partly because they are, very small amount, and plus they are not available as easily as the Apollo samples. And Chang'e 5 has just brought back about 1.7 kilogram of material. And very soon they will be releasing that to the world community so people can apply just on the same terms as the NASA Apollo rockets. But in the last 10, 15 years, actually, lunar meteorites are now altogether coming to outweigh the amount of samples that are available from the moon compared to Apollo rocks. So already 400 plus kilograms of lunar samples are available in terms of meteorites. And because meteorites could have come from anywhere, from the near side, from the far side, we don't know that for sure, from the poles or whatever, they are actually giving us a challenge that, you have to find out where I have come from and what secrets I have inside me. And that's why the work on lunar meteorite is picking up momentum. And one of my PhD students, Tara Hayden, she just passed her degree last month and heading to Canada to work with a colleague called Gordon Olszynski, which some of you may know. They are going to be the leaders who are going to be leading the field of lunar meteorite in coming days. But before we go and say we need more samples, we need to also see what have we learned from the samples that we already have analyzed. right? So I would like to tell you about some of the key findings that have come out. By no means the question is settled, but it's a fast-moving field. But the latest is that there is quite a consensus in the community that the moon had an impact origin. And the model suggests that there was proto-Earth, which was hit by another object, from which the moon ultimately formed. Now, whether the moon formed after the material was mixed within the proto-Earth from that, or moon formed from the material that was flung from the proto-Earth, we don't know the finer details. All we know is when we analyze the lunar rocks and the terrestrial rock, the two have almost identical oxygen isotope composition, right? And that is pointing to whatever makes them was identical. How it came about is subject to lots of modeling and lots of interpretations. So we published a paper in Science Advances, and these two of my colleagues are very well known for their oxygen isotope leadership in the world, Ian Franke and Richard Greenwood. And we did the highest precision oxygen isotope measurements on Apollo samples to, first of all, demonstrate that the moon and the Earth were almost identical in oxygen isotope. And secondly, we used that data to propose that any water that is there on Earth or the moon, much of it must have been present before the impact happened. Otherwise, it will violate the oxygen isotope similarity. Right? And you have to read that paper to know a little bit more about it. I don't have time to go into this. The other thing that we learned from the Apollo rocks is this concept of lunar magma ocean, which has now become the model for evaluating the evolution of any rocky planetary body. Yeah? And so the idea is that after the giant impact or the impact that formed the moon went through a magma ocean phase, and it was simply a big ball of molten basaltic magma, which crystallized the way you know basaltic rock forms from a magma, where more magnesium-rich minerals they form first, more iron-rich minerals form later. And it formed in a stratified manner, where you had things like olivine and pyroxenes forming first, and then plagioclase-rich crust, because of its lower density, it floats to the top. And then in between, sandwiched, is what is known as a rare earth element and potassium-rich layer called creep layer. And you will hear this term creep a lot. And what it is the residual, the very last dregs of that lunar magma ocean that happen to be rich in potassium and rare earth elements because they don't go into a solid phase. They want to stay in the liquid as long as they could, right? But the moon's evolution wasn't that simple. After this crystallization, what has happened is your very iron-rich mineral, such as ilmenite, very high in density, and is now towards the top, and it makes the whole pile unstable. So there was supposedly a mantle cumulate overturn because of this density instability. And when you have that overturn, what you're doing is you are mixing something that formed very early with something that formed very late. And once you do that, then you produce a source called hybridized mantle source, which you then melt to form magmas that form the mare basalt that we see on the surface. Yeah, so I just summarized to you in 10 seconds something that took people 50 years to understand, and we are still teasing information out. But you get the picture what we are dealing with. Yeah? It looks simple, but actually it is not that simple. And every sample that we get tells us a story, a piece of that jigsaw. Okay? And that's what the moon from the outside obviously looks like, your mare areas. These are the lavas. So once the magma ocean had crystallized, there was melting in the mantle that brought magma at the surface. And moon being so heavily impacted, it had so many craters, those craters were filled with these lava flows, which is what we see today. Okay? And the higher regions, which were formed by those feldspathic minerals, they are present in the form of lunar highlands. Right? But what we don't know, what happened to the far side? Because remember, the far side didn't look anything like near side. Yeah? So the question is, will the rocks from the far side reveal the same story? Or is it going to tell us two faces of the moon, so to speak, that one has a different evolution compared to the other, and why? Question is why? Why should we care? Does it say anything about the timing, when that might have happened? And if we know when it has happened, what did it do to what was happening on Earth? Life had already originated on Earth, but if you have heavy impacts recorded on the moon, surely the Earth was also impacted, which might have implications for what was happening on Earth with regards to the evolution of life. So again, drilling down a bit further into more niche area that I have developed further interest in over the last 10 years is revisiting the paradigm from the Apollo days that the moon is a dry, dusty place. It's called a bone dry moon paradigm, where the Apollo sample measurements 50 years ago suggested the bulk moon had 1 parts per billion or less water inside, which means essentially nothing. That's all we could measure. But that view started changing in light of several measurements that were done in 2008, 2007 timeframe. I was already working on a mineral called apatite. That's a calcium phosphate that also accommodates hydroxyl in its crystal structure. Now, we knew apatite occurs in lunar rocks, but we never thought that it could contain any water because there was no direct way of actually detecting it. Neither people were actually, trying to detect it. But in 2008, I heard somewhere that actually people are speculating that they cannot fully account for the chemical formula for apatite. There is something that is called a missing component, and that missing component could be water. And I happen to be at the OU where we have access to an instrument called SIMS, which we also have next door to you, particularly NanoSIMS. It's nano secondary ion mass spectrometer, which can directly detect the presence of hydroxide or hydrogen in your sample. So we analyzed the same apatite. I already, as I said, was working on apatite in lunar samples because they also contain uranium. So you could actually do the uranium-lead age dating using apatite to know the age of the rock. So I had the sample, I had the setup, and all I needed to do was to actually explore the possibility of detecting hydrogen. And lo and behold, we did find hydrogen. And a couple of other groups around the world were also detecting hydrogen in apatite, but also lunar volcanic glasses. And suddenly, all of a sudden, 2-3 papers were published suggesting that actually there is a significant amount of hydrogen in lunar samples. Almost creating a race for everybody to reanalyze the lunar samples once again. That was the paradigm shifting moment. But of course, at the same time, Chandrayaan-1, moon mineralogy mapper data was being used, the deep impact data was used, the Cassini data was being used to argue that there was a thin layer of hydroxyl or H2O all over the lunar surface, particularly in hand signature near the lunar poles. So suddenly the water on the moon story picked momentum, both from the remote sensing, so it's official expression, but also from sample science for things that we were doing. Samples telling us that inside the moon also there is water. And the two together, it just ushered in a new era of lunar research. And we were always asking, why are we doing this? What is the question we are trying to address? How we are going to do it? Because as a scientist, you have to answer these questions before you actually embark on a very long journey. You have to convince yourself what exactly are you trying to find here and how you're going to do it, right? So these are some of the questions we were trying to address, and which is what we are still involved in. Made a lot of progress, but a huge progress is still to be made by many of you sitting here. The detection of water in lunar samples started with volcanic glasses and apatite, but as our understanding and the laboratory analytical skills improved, we actually started to use the instrument for detecting even lower and lower quantities of water and its isotopic composition. So then we started focusing on things like melt inclusions in basalt And more recently, we have been looking at things like nominally anhydrous minerals, such as olivine and pyroxene that contain as little as 5 parts per million water, right? Which were very difficult to do even 10 years ago in these things. So we have come quite far down, and this is just a boring slide to show you that nothing is perfect. If you look at appetite, it has got some pros, but it also has some cons. If you look at melt inclusions, MIs in basalts, again, it's good for some things, but it has got certain complications. Nominally anhydrous minerals are good, again, but then they suffer because of the low amount of water that is present in them. So if you want to measure their isotopic composition, it is subject to what is known as spallation correction. And because the moon has no atmosphere, any material on the surface is directly affected by cosmic radiation, which produce excess deuterium. Now, in order to know the true deuterium-2 hydrogen signature of the lunar sample, you need to know how much of it has been produced through spallation. And it's not a trivial task, okay? Whereas if you have 100 ppm water or more, you don't necessarily need to know the cosmic ray spallation correction because it doesn't make much difference. So this chart just shows that you cannot just use one system. You have to use a multiple approach, and hopefully you arrive at a coherent picture, which you can then communicate as a single story, okay, which is what we are trying to do. These are just some of the pictures to show what we have targeted so far. So you see a picture of an apatite in a thin section surrounded by plagioclase and olivine. These are all in situ work using SIMS mainly, sometimes nanotins. The melt inclusions, not very pretty, but with lunar samples, you don't get to pick. You don't say it's not good, I'm going to go tomorrow to field and collect more samples. No, you don't, right? You can't even polish too much any of the thin sections without prior permission of NASA in case you actually waste the materials. So you have to be very careful because these are such rare and precious samples. But you do all what you need to do within the given parameters. And then the ultimate aim is to either find out the origin of that hydrogen, which we try to ascertain in terms of its delta D value, which is deuterium to hydrogen ratio compared to a standard mean ocean water in this case. I'm not going to talk about chlorine. That's a separate story in itself. But chlorine also has been providing us with some very interesting insights. Before you actually go to the story, I already mentioned to you about spallation. You have to control the effect of spallation. But there's something else that's happening in lunar samples. It's called degassing. So you have a magma coming up on the surface, and the surface of the moon is almost open to near vacuum of space. So any magma coming on the surface is going to lose the volatiles, particularly hydrogen, because it is the lightest element that you have. Now, hydrogen has two isotopes, hydrogen and deuterium. Deuterium is twice as heavy as hydrogen. Near the lunar vacuum of space, you lose much more of the lighter hydrogen compared to the heavier, and therefore giving you an artificially high delta D signature. Yeah? And what you need to do is you need to model it, how much degassing has happened under what condition to actually get to the actual original P2H ratio or delta D values. And sorry, this one I was pointing for the wrong one. This is the one I should have been pointing for the degassing, and that's the spallation. Okay? So that's the effect of spallation. When you correct for it, you come to the right value, but if you don't, then you are going to make a wrong interpretation. And the same with degassing. If you don't actually correct for the degassing effect, you are again going to make a misleading interpretation. So these are just some of the examples of how difficult some of these studies have been. Anyway, we did all of that, and multiple PhDs and postdocs, and about 5-6 years ago, we thought that we got to a good story. We understand the history of water in the moon. And at that point, Jess was just finishing her PhD. She is now an assistant professor at the University of Arizona, and just compiled all of her data and used a model using the known compositions of various chondritic materials, how much water they contain, And we propose that much of the water that is present in the moon looks like as if it has been derived mainly from asteroids. Because up until that point, there was a big debate whether it's comets or the asteroids. So at least we were able to show that with all the data that we had until that point, the story made more sense if the water in the moon and by extension on the Earth was mainly derived from asteroidal sources. So that was 4 or 5 years ago. The story has become a bit modified in light of recent data, and I'll show you that. And this is where Alice's works come in. So Alice Stefan was a postdoc with me until just before the pandemic. She's now a Marie Curie Fellow in Rome. And Alice really was the leader in setting up the analysis of nominally anhydrous minerals, very low detection work using our nanosynths. And what Alice found was that there was a correlation between the delta D values of these minerals in which she was making measurements against the titanium oxide content, bulk titanium oxide contents of the rock. And I don't have time to go into the detail, but what it is showing is not only there is a correlation, that correlation suggests that the lunar magma ocean itself underwent some form of degassing, hydrogen degassing. And remember, I told you that when you have degassing on the moon, if the hydrogen is degassing, you raise the D2H ratio. Yeah. So this is what is in the real samples. The question is, can you use this to get back to what was there before the degassing happened? Yeah? And that's where you can use 2 approaches. Either you regress it to almost no TiO2, the bulk magma ocean, yeah, or you find a sample that really was the very first one that formed after the magma ocean started to crystallize, meaning it has the minimum signature of degassing because it was the very first one to have formed, right? And from both tests, we find that actually the delta D of the proto-moon was somewhere around negative 450 per minute. And if you remember the previous slide, we said it was between minus 200 and plus 200. And now we are finding that the proto-moon was more like minus 450. And if proto-moon was that, then the Earth was also negative 450. And there are independent evidence that the proto-Earth or the early Earth did have negative 450. So these are independent studies. These are not our work, but other people have found evidence in some terrestrial rocks where negative 450 has also been proposed. So next question is, where is it actually this coming from? Okay? So at the moment, this is a developing story. It is not yet published. It's in review. And there are a couple of options. One could be that the impactor that formed the moon itself brought that signature. It might have formed very early when the nebula was still around, and the solar nebula would have a delta D of negative 900, right? So if you mix that material with something which is heavier, you could produce this, or you might have had deuterium poor ices in some of the asteroids that had actually delivered water to the Earth system. Yeah. We can't say for certain which option was right, but we think that the nebular option seemed to work better than the D-rich ices in the chondrite. Okay? So that again is an evolving story. Somebody earlier today was asking me about if we go to the lunar poles, you may find organics, you may find few other volatiles. Yeah, if we get the samples, we might actually find if there are any organics or any signature of deuterium poor ices, we might be able to see from the lunar polar region. Then we have to modify our models. So that's where I want to leave the sample-based research and move a bit into more exploration side of things, because I think maybe the science side of things or the sample side of things is not interesting to many of you because it's a bit esoteric and it's, because this is what I do, so I enjoy most. But the exploration side of things is what is exciting the rest of the world at the moment, is the potential possibility of going to the moon once again, but in a more sustainable manner. What that means is when humans return to the moon, they will stay there longer and they will utilize the resources that are already present on the moon. And the first and the most important resource in this context is water. Because we know that if humans are going anywhere, they will need water to survive. And we also know that water is useful in many of the processes that we use for our daily living. Okay, so that's why finding water at the lunar surface, and that's why the work that somebody like Christian, they are all doing is so important. And this is what is driving the next phase of lunar exploration. We are also doing research on extracting the water from the lunar rocks themselves. What if you go to the lunar poles and you don't find this water ice that you are expecting? You should be technologically prepared to say, I didn't find water I was looking for, but I can extract that water from the rock that is out there, right? So we are also doing that experiment at the Open University to do that. But right now, I'm going to take you on a journey where actually, let's believe that the remote sensing data that we are looking at are actually pointing us towards the presence of easily accessible, some form of water near the lunar poles, okay? So this is a very famous image from Carly Peters' 2009 science paper from MQ dataset. And what you're looking on the right-hand side is a false color image where you see these three craters lined up, and the bright bits are the suspected water ice, the pure water ice near the surface. Nobody really knows for sure, but that's what is suspected. And there are a whole swathe of other measurements from orbit that have been done to show that near the poles, and these are all pole views. So we are looking from the bottom towards the south pole of the moon. There's some of these craters near the south pole. It contains water ice. Within the first meter, maybe first a couple of meters, which is really easily accessible if you can get there. But the environment in these craters are extremely difficult because in some of the craters, the temperatures can go as low as 25 Kelvin. And so far, I don't know any machine, any robot that actually can operate in such a low temperature. So again, the quest is on to find water ice in other areas near these permanently shaded regions. Yeah, things like micro cold traps. Yeah? So we will see more data coming in. But before you do it, NASA thought it's a good idea to actually at least try to confirm further if there is really water ice. So they did this impact experiment called L-Cross, where they hit one of the polar craters in the moon near the lunar south pole called Cabeus crater with a spent rocket. And the plume that came out from that impact was then measured using a number of instruments on a shepherding spacecraft, and they detected about 5-8% of water ice. So it does look like there is some water ice, but again, that's one spot on the moon and not a huge amount of water either. And there was a big uncertainty on those measurements, but we are still going in the right direction. So now the next phase is that NASA would like to send a lander using a commercially procured program called Commercial Lunar Payload Services, CLIPS in short, they call it. And it's a mission called Viper that is due to be launched. It was going to be launched later this year, but maybe it will go next year. These things keep shifting all the time. But the idea about this mission is it will land near the Cabeus crater in that area to actually find the ground truth, what is there. And if it does find water ice within the top 1 meter of it, then I think it will accelerate the lunar exploration hugely. To do all of this requires a lot of effort, patience, planning, and that's what has been done using something called Global Exploration Roadmap. This is something that the space agencies like to talk and always try to shift it 5 years down the line. But at least the idea is to actually integrate exploration of one body with the next and to have a view where we are heading next. Okay, and in this view graph, you will see it was showing that between 2020 and 2030, we would have already gone to the moon and we would be moving towards Mars. Well, that's not happening at the moment. I think we are probably 5 or 10 years off from there. But it gives you a sense of where the global exploration strategy is moving. And sometimes scientists like us, we get invited to actually contribute from the science point of view. That if we did this, then what would be the science benefit, or what would be the science drivers for some of these strategies? Okay, and out of that, something called Artemis Accords has emerged, where the next phase of NASA's lunar exploration is termed Artemis, and NASA wants other countries to join them in this endeavor, and lots of countries have actually formed a partnership. European Space Agency surely is participating in this program, but there are other agencies like JAXA and a few other Australian space agencies and others also have joined in the effort. And ultimately, it will move towards something called a lunar gateway, which is like having a space station around the moon, like you have the space station around the Earth. And again, we can go into some detail if need be, but we don't need to. The idea, if you understand, is that humans, when next time they go to the moon, they don't directly go down to the surface. They might stay in the gateway until it is required that actually they land on the surface, or it might be used as a staging post. If anything is coming from Mars, it can actually be staged there for some time before it is released to return to the Earth. Or it can be used for astronauts teleoperating rovers and landers on the lunar surface. So multiple purposes. And they would be much safer, relatively safer in the gateway than being on the lunar surface until they can build their own habitats. And that's where the resources comes in. Okay? So in order to survive at the moon, you need to utilize the resource that is there. And at the moment, the best resource and the only resource that we are aware of is the lunar regolith, which is a loose material, covering the entire moon up to a depth of at least 2 or 3 meters. So the question is, how can you use the lunar regolith? And for that, you need to develop or bring all the knowledge that we have gathered from the last 50 years into the context of space resources. So I played a small role there by leading a team for ESA that led to the development of what is known as ESA space resource strategy. And we are using that as a basis to actually build the future program. So I told you that lunar regolith is your resource. And lunar regolith is nothing but broken down rocks. That's all it is, right? And most of you probably are from geoscience background here. So when we are talking about rocks, we are talking about minerals, we are talking about elements. Yeah? And half of the lunar regolith actually is comprised of oxygen. And oxygen is one of the most expensive or sought after commodity for human survival. Yeah? So you have got a resource at your hand that contains half of it is oxygen. It's up to you how to extract it. So there are lots of experiments going on to come up with the ways of extracting this oxygen. If you can then combine that oxygen with hydrogen, you have the next commodity that you really need. That's called water, right? Whether you bring hydrogen with you, it's much lighter, so it's much cheaper to carry, or better still, and my hope, is we find hydrogen on the moon itself. Then you need to understand where that hydrogen might have come from. Well, there is something called the sun, which is constantly supplying hydrogen to the lunar surface. But you need to find a geological process that can concentrate that hydrogen in sufficient quantities that you can then exploit for the purposes that you seek. So some of the research that is going on, the fundamental research, like I showed you in the first half, is guiding us about the potential sources of hydrogen. Not only where they are, but where ultimately they might have come from, so that you can find out how much reserve there might be. And it is then driving the exploration strategy, because you need to get that hydrogen and oxygen for human survival. And for that, we are also sending some labs, I mentioned at the start, to the lunar surface to make those measurements so that we can be more confident in suggesting the strategies that we have. And here are a couple of my colleagues. So James was my PhD student, Hannah was also PhD student a few years ago. And Sim Barber is the leader of that group where they build the space instrument. And both Hannah and James worked in that group to build mass spectrometers that can be sent to the moon one day to do the measurement of water ice that is present on the lunar surface or demonstrate the extraction of oxygen by heating the lunar regolith. As I said, if the water is not there, you should still be able to produce your oxygen or hydrogen. So we will do both experiments on those missions. Beyond that, we also want to explore the possibility of using microwaves for processing the lunar regolith, for building our habitat using 3D printing. And this is the work that has been led by my colleague, Sangwoo Lim, and our two PhD students here pictured there. So Vibha is now back in India. She did her PhD in actually coming up with the idea for an industrial grade microwave, and she saw the commissioning of it, and it took her a long time, but she persevered. So all credit to her. And James is right now using the same setup to find out that if you have water ice in the lunar regolith, how efficiently can you extract, how much power, microwave power you need, and how long you need to heat it. And it's a work in progress, but of course, this is what attracts journalists. This is what people like to cover in newspapers. So BBC would rather cover this story than my science story any given day, okay? Because it connects better. And of course, then you go to newspapers, they come up with these kind of titles because everybody will like to read the article then. So this is last Christmas, a story that was run in a national newspaper called The Guardian in the UK, where they described our work for doing the experiment for extracting oxygen from lunar rock. And it's a great advertisement because this is the sort of thing that actually a common person who isn't involved directly in science, but actually paying my salary, paying my research grant, would read and hopefully feel good about it. But also, they will share that knowledge with somebody else, and it might inspire and excite others to then get interested, right? Or the politician, on their coffee table, they might read the paper and say, oh, these, crazy people at the OU, they are doing that. We need to talk to them to get a different view on their daily lives, right? Which is always quite complicated. So this is where the future of lunar research is moving. New samples are becoming available, whether it is Chang'e 5 or it is the reopening of, or opening rather, of Apollo 17 cores by NASA program under a program called ANGSA, which stands for Apollo Next Generation Sample Analysis. And this is where early career researchers, PhD students are given the opportunity to work with Apollo samples as if they are new samples until the new ones arrive through Artemis. Constantly, we are developing new methods using analytical instruments. Ideas for new landers, rovers are being developed in the spirit of ultimately realizing the living of the land concept. But it is not for everybody to go to the moon just for the sake of it, but it is for explorers, scientists to go there for extended periods of time in a sustainable manner. And there are lots of other things that will follow from it. And of course, I mentioned to you the Next Generation program. And these are the recent pictures from the first Artemis one, the launch of the Space Launch System, the SLS, back in November 2022, and the beautiful picture that it took by going way further down beyond the moon and then looking towards the Earth with the moon in the foreground. And a beautiful picture. Artemis 2 is going to take 3 crew members to this point, which no humans have ever gone before. So I think Artemis 2 will take them the dress rehearsal for the eventual landing to Artemis 3 in 25, 26 at the South Polar region. So of course, a successful recovery in the form of a splashdown is always the key, which is what happened. And nothing would ever be complete if you aren't able to actually share that excitement and passion with people of all ages and from all backgrounds. And we do lots of outreach activities. You all, I heard, do a lot of outreach activities. You will be doing some in the next day or two. But this is just some pictures from a summer science exhibition that I led at the Royal Society in London, where we had around 15,000 people come to talk to us, see what we were doing, put on the VR headsets, walk on the moon, hold the moon rocks, or sometimes some simple things work, just take a moon globe and just get to the level of the person you are talking to. In this case, a very young person just interested in handling the globe. So you want to get them engaged. And I just love this. And that's why I have set up an outreach program that happens every year at UOU called the Moon Night. That happens every December. We broadcast it live, and we try to give people as much chance to actually participate. But of course, you have to be there to physically hold and handle the thing. So that aspect is not available virtually. And one of my students actually came up with this logo for living on the moon, and I'm very proudly wearing my T-shirt that we designed. And this is all in the hope that we can actually engage in a dialogue with anybody who is interested. And finally, if any of you are interested in learning about not just the moon, but planetary science or anything, you can go to a website called Open Learn. It's free. You don't have to pay or register or do any of that malarkey. Just on Google, you put Open Learn, and on Open Learn, you can find all the free content that actually you are looking for. And you can search for keywords, etc. And if you really are a mineral nerd, then one of my colleagues and I have put together a downloadable version for iPad and tablet and everything for all the minerals that have ever been reported from the moon. Okay, it's called Moon Minerals. And please consider coming to the Lunar Symposium, either physically or virtually. It's a hybrid meeting. The deadline for abstract submission is in 2 weeks on 8th of March. And we are really looking forward to innovating the next edition of European Lunar Symposium. So keep your eyes and ears open. And I think with that, I need to thank all those agencies who have given me funding or who have trusted me with their money so that I was able to actually do the research and able to supervise all those students and postdocs. And I think I am done. So thank you, and I'm happy to have any questions.
Thank you, Professor Anand, for this fascinating Vyakhyaan, and wherein you took us through not only your journey of research, but also the various aspects of lunar research, the current status, the future directions, and so on. It has really been a very wonderful lecture and in a very nice informal fashion. You put it very complex results in a very nice. I know your slides. I like your slides very much. Thank you. I'm sure there are a lot of questions. To conduct the question answer session, I'll request my colleague, Professor Varun Sheel, to conduct this.
Thank you, Professor Bellangaja. Interesting journey and all that we need to know about the lunar science and exploration. So the talk is now open for questions. Please raise your hand. Yes, Dr. Gibson.
In one of the pictures, when you're showing far side of the moon, it looks far more uneven than the front side of the moon. It is terrain height with the feet. Yes, sir. Does it have to do something with the Earth that the front side gets less inclined? Or why is that?
You mean for the difference in the far side and the near side?
In the terrain height.
Terrain, yeah. It's much more cratered, isn't it? The far side, it looks much more cratered. So there are lots of theories, and one of which is that the near side somehow had a thinner crust because of the preponderance of this creep that I mentioned, the potassium rare earth element rich layer. The potassium is radioactive, uranium also is sometimes radioactive. That is what produced the basalt that we see on the surface. And the thinner crust actually facilitated that, because of which you now see the flat lava plains inside the big craters. Whereas on the far side, the crust was way thicker, and that has been confirmed by the Grail mission, for example, where the crust is much thicker on the far side, that any melting, even if it happened, couldn't bring the mare basalts on the surface to flood those craters. Or maybe the creep layer is not global. The creep layer is only concentrated on the near side, not on the far side. But if we have rocks on the far side, we would be able to confirm whether they are from a creep source or not, because creep has a very specific isotopic signature for things like neodymium isotopes, strontium isotopes. In fact, that is one of the big things that has come out from Chang'e 5 results. I mean, one would expect that Chang'e 5 samples are coming from the near side, from those lava flows. And because the rest of the Apollo samples were creep-rich, this should also be creep-rich. It's not the case. Yeah. So right now we are trying to explain how that might be the case. Forget about the far side. Even the near side is
It
not
has
clear.
nothing to do with Earth. I mean, for example, like we know that tides are affected by the moon, so same way the Earth may be having effects on the Earth.
Yes, and could possibly, because the moon was also a lot closer to the Earth. You know, the moon is receding, going away from the Earth. So the effect of tides on the moon would have been much stronger in early days, you know, at 4 billion years or 3 billion years than it is today. So that's also quite a possibility that you have tidal heating that cause more melting on the near side compared to the far side. Yeah, that's also a possibility. But there are some other impact theories as well, which is called, in one of the models that I was reading, that they have an hit and run collision, where you have a hit and run collision, and the next collision that happens, it actually punches on the far side, but actually the effect is seen on the near side. So there are lots of models, but actually really what we need is some real material from the far side to put to bed some of these theories.
Thank you very much.
Sure.
Dr. Sajid.
Thank you very much. It was really a nice talk. I have a question regarding the regolith thing. So you're basically talking about this oxygen bonded at silicates,
Yeah.
and then somehow it's getting combined with hydrogen to produce H2O, right?
You first liberate that oxygen
Yeah.
from the silicates and then combine it.
So how do you do that? Like, how do you foresee that it can happen on surface of the moon?
Well, you can, you can pyrolyze.
So it's at a very high temperature, right?
Yeah, of course. Yes, yes. So that's one way of doing it. The other way that was originally proposed was you have this mineral called ilmenite. And it was proposed that actually at relatively lower temperature, and I'm saying lower temperature, but still you need, more than 500 degrees Celsius, close to 900 degrees Celsius, where you pass hydrogen over ilmenite, and actually that reduces, and that gives out its oxygen, and you produce water. So that is very well-known reaction called ilmenite reduction process. One of the demonstrator missions that we are showing, so I showed Hannah Sargent, mentioned her work. One of her work was to actually do the ilmenite reduction. What we found while doing that, one day I asked her a question. So if somebody said ilmenite, we just focus on that. What else is there which is similar to ilmenite in a lunar rock? Okay, there are something called spinels. Why are we only looking for ilmenite? What if you have spinel-rich rocks? Because your highland rocks don't contain ilmenite, they contain spinel, right? And until that point, everybody was saying that in order to do this production, you have to go to Mare region because that's where ilmenite is. And I want a process that can be universally applied. I said, no, I want to go to highland region. If they have spinel and ilmenite are not very different. Can we do the experiment to see whether we do the same thing? And we found that actually spinels do reduce as well. And then we also were looking into reducing the actual silicates, which will require higher temperature. Yeah. So it's a multi-step process. Thank you.
So just one more thing, like, I'm just curious. So you're talking about near and far side of the moon, and the differences in that basically literally of near and far side is very interesting. But why do you think the mechanism of the formation of two sides of the same object can be different?
Million-dollar question. I think if you form the moon in isolation without the influence of any other bodies, you might expect it to form in a homogeneous. Perhaps the way that it is tidally locked to the Earth, that it locking with the Earth had an effect on how the near side and the far side is formed, followed by the impact processes because they are random, chaotic, which then might have added to that complexity. Yeah. So these are all conjectures. I am not a dynamicist. I'm not a modeler. So I don't know. All I know is I need to reconcile the geochemical signatures that are preserved in the samples with the model that others are proposing that the moon had. Right? So I want to contribute from that direction, but the other side is for somebody more learned than me to actually solve.
Thank you, sir, for your nice informative talk. I have a question regarding solar wind interaction with the moon's surface, because you mentioned that solar wind proton may be the possible source of hydrogen in moon's surface. So the question is how solar wind as a whole interacts with moon's surface, and how this interaction affect the isotopic composition in surface layer.
Right. Good question. I think you have an expert here at PRL who is working on exactly that problem. So I encourage you to actually, I will connect you with them if you don't know them already. But in short, the idea is that because the moon almost has no atmosphere, right? It's called exosphere. So any cosmic ray, even the solar wind protons, they can reach the lunar surface very easily. Yeah? And these are some of the very high energy particles. And when they come and actually impinge on the surface of the lunar material, they are sputtering the other elements that are present in those silicated structures. And they are creating what is known as unsatisfied bonds or dangling bonds, sometimes they are referred to as, where the oxygen is hanging there with a bond and waiting for a proton, for example, from somewhere to combine. And that's what the solar wind does. Now, once the hydrogen or a proton gets attached to the oxygen, you form that hydroxyl, it then gets locked. Okay? Then it's not so easy to remove it. Right? And this process goes on and has been going on for billions of years. And once it is locked in there, micrometeorite impact will garden it. It will actually take it from the surface, put it down, bury it. Then the next fresh surface is exposed to the, again, space weathering processes. This is what we think is happening, but I'm sure your colleague will tell you, or your professor will tell you that it's a very complicated process. We are getting into that phase of interaction of cosmic radiation with this solid material.
Thank you, sir.
Sir, this is regarding microsintering and a quite similar question to the previous one. And also we had some discussion morning. So with like about a kilowatt of power and lots of temperature there in the sintering process, you just mentioned that one of your students is now working in the extraction of the water from the simulant. So I'm just wondering if it is shareable. No, the techniques, how you extract really in the laboratory, or how you plan it to extract.
So in simple terms, what we do is we have a crucible, which you fill up with your mix. The mix is your simulant with water that has been cooled down using liquid nitrogen to the temperature that you want to use it. And in this case, it's simply a matter of actually adding the water and cooling it down. But then he's also looking into the presence of water ice in different forms. Is it present as lenticular ice? Is it present as diffused ice? Is it present as granular ice? In what form is it present? So he's going to the next stage. But in simple terms, the very first experiment is to actually wet the simulant under controlled condition, cool it down, put it in the microwave cavity. You then heat it up, and then we have a whole pipeline attached to it where you have cryo trap. When The heating happens, obviously the water is released. The water then is channeled through these pipes, is trapped into a cryo trap, which is then either released or you see the pressure difference. And that pressure difference tells you the loss, and you equate that loss of pressure with the loss of water that you have previously calibrated. Yeah. So there are 2 or 3 different ways of it. We haven't yet got to where we actually put in a gram of water and we collect that gram of water. So that end-to-end demonstration is yet to happen because it's so complicated. Each step we have to perform. So we are using the change in pressure to show that actually the volatiles are being released. We then also want to know the isotopic composition of that volatile that we just released eventually. Yeah. So we got the lab is quite full of pipelines and various things. So it's a work in progress, and you're welcome to visit and see that. Yeah. Or one day I can ask the student himself to give a talk if you are interested.
You talked about the Chang'e 5 discovery regarding recent volcanism. So now there's a complementary view as to how this volcanism has originated, and it's not related to the creep, the presence of creep or enhancement of uranium, thorium, potassium, and the rare earth elements. So do we know the potassium, thorium, and the uranium concentrations on where Chang'e 5 landed, so that we can make a heat flow calculation and then link it with the amount of heat required for a volcanic event? And there's also a paper by Amit Basu and his colleagues on some rocks, lunar rocks, which we collected from sample return mission. So do you think this has occurred continuously through, say, between 2.7 billion years till about 3.8 billion years, or was it episodic, or we need to know more? We need to have more missions which will look at uranium, thorium, potassium at various locales and consider whether the volcanism which is being talked about is related to creep volcanism or not. I mean, it has the last word basically been written on this idea.
Not at all, not at all. So I think the sampling is incomplete, to say the least. At the moment, all we can say that it is episodic because all we are seeing are gaps. So up until the Chang'e 5, the youngest basalt ever dated was around 3.1 billion years. There was some reports of 2.7, 2.9, but it has really not been verified. The youngest was 3.1. After that, Chang'e 1 at 2 billion years is really the youngest one. But there is a gap of 1.1 billion years. Okay? Are we saying that actually there was no volcanism between 2 and 3.1 billion years? Maybe, maybe not. Most likely not. Right? Because if you trust the remote sensing data, the work that my colleague Harry Hiesinger and others have actually produced with model edges, they have actually shown the possibility of lava flows of different ages all the way coming to almost a billion-year-old. Yeah, we haven't sampled those, and it's not so easy. On the question of creep, Chang'e 5 actually was targeted for the very reason that it was going to a creep-rich region to collect the creep sample. And it is high in potassium and rare earth, no doubt about that. But that potassium and rare earth element enrichment has happened, seems, because of extreme fractional crystallization, not because of the creep contamination from the original creep layers. Yeah? And so it needs another explanation. And what is near the very surface is not necessarily going to tell us about the heat that is there in the mantle source region. Yeah, so it needs a little bit of more extension of some other knowledge. So with the Chang'e 5, I think the jury is still out. People are still, Yeah, sure. But uranium and thorium, again, you can, thorium is not as high. No, I don't think so, but I'm not 100% sure. All I know is that when the actual measurements for thorium and uranium were done, they were not as high as you would expect in creep, but they were still high as you would expect in a fractionally crystallized basalt. Okay. The other speculation was that maybe there was a lot of water present in the source region of Chang'e 5 samples because water can lower down the melting temperature. I just showed you the nature paper. It is telling us that actually it is one of the driest source regions. Yeah. So we ruled out the possibility of water being involved. We ruled out the possibility of creep being involved. So what is it? So the only other thing that comes to mind is what I started doing my PhD with, which is called decompression melting. Right? But decompression melting happens on Earth, where there is lithospheric stretching that is going on. So how do you cause decompression melting on the moon? You then invoke impacts. Right? So I don't know the full answer to that, and I don't think anybody really knows the answer to that. But the next few years, I think the efforts are going to be focused on better understanding that in the absence of water, in the absence of heat-producing elements on the Earth creep, how do you create lunar volcanism up until recent times, right? So it's a fascinating problem to have. And the work that you refer to of Amit's, I think I came across very, very recently. So I have to read the paper in full. I think they worked on some lunar meteorites that were collected from Antarctica and compared it with a few others. I think one of those I worked on, Kalahari 009. In fact, I was the first one to date it as 4.35 billion year old. So that looked a very interesting paper, and it may be providing us with some clues to how we might interpret the data on missions like Chang'e 5.
So from the live questions, you go to the YouTube. So these questions, I'll have to read it to you.
Yeah.
This is a one-way communication.
Sure,
So
sure.
they'll be able to listen to your answer.
Yeah.
So first question is by Mansa Goda. Can we expect any microorganisms on the moon?
Possibly not. I hope not. Especially that the astronauts haven't actually left anything that is still survived, because the highest chance of finding any microorganisms is probably humans actually taking them. They say microorganism or micro, yeah. With them when they go to the lunar surface, because as far as we know, conditions of the lunar surface, the radiation environment, and the rest of the conditions are not conducive to life as we know it. Yeah. But remember that I put a caution right at the beginning that never say no. But I think right now our scientific understanding is so poor in that area that we can't even start to speculate. So all the evidence suggests that it is highly, highly unlikely.
Yeah, the question is by Basavaraj. What is the current thinking about the origin of the moon? Basically, is asking on the origin of the moon.
Yeah.
What is?
I think it's are they talking about the impact origin of the moon, presumably? And so
I think so.
we think that the moon has derived from a material which is very, very close in composition to that of the Earth itself. Somebody could argue that you could bring the moon and the Earth forming from the same material, but separately. That has been looked at. But all the dynamical calculations and simulations and the isotopic measurements that we are making seem to suggest a close involvement of materials before they went their own way, so to speak. Yeah, so that's the current.
So thank you, Professor Mahesh Anand. Let us thank the speaker for a very interesting talk. And please open for questions. We will be here after this, so anyone who is interested. So now I request Dr. Durga Prasad to give a vote of thanks.
Thank you very much, Professor Sheel, for giving me this nice opportunity to propose vote of thanks for the speaker today. I'm immensely pleased to propose vote of thanks for today's speaker, Professor Mahesh Anand, who has delivered the 77th PRL Amrut Vyakhyaan. Of course, it's second in our phase 2 series of Vyakhyans. Thank you very much, sir, for illustrating us your journey of science and also taking along with us the journey of exploration of the moon and elucidating us about the evolution of the moon, water problem, challenges, future avenues and ideas for exploration. Thank you very much, sir, for accepting our invitation and delivering our 77th Amrut Vyakhyaan. I thank our director, Professor Anil Bhardwaj, for his continued support, which is being fueling us to take this Amrut Vyakhyaan forward with the same enthusiasm in phase 2 as well. I thank our Dean, Professor Pallam Raju, for his constant guidance and suggestions. I thank Professor Nandita, Chair, and Professor Lokesh, Co-Chair of PRL Amrut Vyakhyaan, and all members and all others behind for making and continuing this Amrut Vyakhyaan a success event. Last but not least, I would like to thank all of you, our audience who have joined here in person for this event, and also all those who have joined live on YouTube channel and your participation and interaction. With this, we come to an end of another interesting Vyakhyaan in our Vyakhyaan Mala. So with this, we sign off for today and we'll be back in the same forum with another interesting Vyakhyaan. So please stay tuned for the announcement of the next Vyakhyaan and also follow PRL on its website and various social media platforms. Thank you very much. I also invite you to join us for tea in the outside auditorium lawn. Thank you very much.